This whole chapter then is dealing with properties. And the big properties are pressure, temperature, specific volume, internal energy, enthalpy. And although it's in the tables, we haven't been introduced to it. We'll get to entropy when we do the second law, but it's a property that you see out there in the tables anyway. But we're introduced to all of these properties. That's not the only properties of a substance. Substance also has C sub P, C sub V, the ratio of C sub P over C sub V. And so we can recall the definition of C sub P. It's the rate of change of enthalpy with respect to temperature holding pressure constant. It's a definition. Sometimes you just have to memorize definitions. This would be the rate of change of internal energy with respect to temperature holding specific volume or volume constant. Okay. If I have a closed system, either the specific volume is constant or the total volume of the system is constant. Either one works. Because if it's a closed system, the mass in the system is constant. So sometimes you'll say, whoa, hold it. Why are they claiming that the specific volume is constant if the volume is constant? Because they're one and the same for a closed system. Are there other properties that you've been introduced to already other than these? Yeah, compressibility factor, Z, you consider a property. You could consider the critical temperature, the critical pressure. Somebody says, my substance is oxygen. Can you tell me oxygen's critical pressure? You know, the critical point pressure, a critical point temperature. Those unique temperatures at that point. Also, the triple point temperature and the triple point pressure. Those are properties of substances. There's just a lot of properties, but the main ones are here. Okay? And why are properties so important? For our type of systems that we deal with, simple compressible substances or systems, then two independent intensive properties fix the state, and then I can get other properties theoretically. Okay? So the state postulate is very important. Quick review. I wanted to put this plot together earlier, but I didn't. So what do we have here? First, on the x-axis, it's a measure of coldness to hotness. You know, there's a lot on here, okay? But it's going this way. You have a sense of cold to hot. So when something's really, really cold, you typically have a low thermometer reading. The thermometer is reading a temperature scale. We know 4 temperature scales at this point. You don't need to know more than 4 temperature scales for the rest of your life, I suspect. But there are other additional temperature scales out there. Don't ask me their names. I just know they exist. And it's like, how many coordinate systems, you know, are out there? There's more than just Cartesian. Oh, there's cylindrical and spherical. There's more than just those 3. But the vast majority of us don't need any more than really 1 or 2 of those, and maybe 3 of those at times. But there are really toroidal coordinate systems and all kinds of crazy coordinate systems. Anyway, so on the x-axis, you get cold, 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 but you can only get so cold. And then you hit a place called absolute zero temperature. You cannot get colder than that. Is that true? That sure looks like a challenge, right? Somebody challenges you, like, I don't think you can bench press 150 pounds. Let me go in the gym and try it. Okay, I don't think you can bench press 400 pounds. Let me go in the gym and try it. Anyway, a lot of physicists are in gyms trying to get below 0 Kelvin, but they can't. They're getting closer and closer to it. So this is an impossible region. Is there an impossible region where you can't get hotter than hot? You know, is there a hottest hot and then nothing hotter? Not that I know of. So now what we did was we said, what are those numeric values on a temperature scale? A Fahrenheit temperature scale, it's plots like this. You get a numeric reading depending on how cold it is or how hot it is. And there's another line for Celsius, Kelvin, and Rankine. All 4 of those are on the same plot. And so at, let's say, whatever place it is, let's say at the ice point of water. Water's ice point at 1 atm. That's cold, right? So it gives a numeric value of 0, in Celsius, a numeric value of 32 in Fahrenheit, a numeric value of 273 in Rankine, and a numeric value of 492, Kelvin, and then 492 Rankine. Okay? These are all the same hotness, coldness, but they have different numeric values for their temperature scale. It may seem obvious. Then you go out for the boiling point of water at 1 atm, 100, 212, etc. Okay? And then you work your way back to absolute zero, and you get Fahrenheit. You cannot get a temperature scale below negative 460 Fahrenheit. Somebody tells you I got temperature negative 500. What word do you use? Impossible. It's not possible. Somebody says I got a temperature of Celsius of negative 300. It's impossible. And below 0 Kelvin, 0 Rankine, it's impossible. So those, they stop there, but they really don't stop out here. They keep going. What's interesting is the slopes. Two of these lines, Celsius, has the same slope as what? Kelvin. And that's that idea of if I have a temperature change of 1 degree C, it is the same change of coldness to hotness, the same temperature change as 1 degree Kelvin. They have the same slope. Okay? Who else has the same slope? Does Fahrenheit have the same slope as Rankine? Yeah, they do. All right? And which one's steeper? Meaning that you get a larger numeric value for the same change in hotness and coldness. Okay? So the Fahrenheit is 1 degree C change is equal to 1.8 degrees, almost 2 degrees Fahrenheit change. It's more rapidly increasing, a steeper slope in the Fahrenheit and the same slope for the Rankine. These two lines intersect on the Kelvin and Rankine are an absolute scales. Where do they intersect? 0. They have the same numeric value at the same coldness, the absolute limit of the coldness. But these two, well, they cross somewhere, don't they? And where do they cross? They did cross at negative 40. So they have the same hotness, coldness at the numeric value of negative 40 C is equal to negative 40 F. So there's a lot of information tucked in on a plot like this. You could put in here, what's the temperature change going from the 0 degrees C, the ice point of water, to the boiling point of water. So in Fahrenheit, it'd be 180. In degrees C, it would be 100 degrees. So that helps you remember, 100 degree C change is equal to 180 degree F change. So I think this is all a review, but I wanted to show you this plot. Also, this is a common plot that I didn't show you, but it's very helpful. What do we have here? We're showing Q, the amount of heat added per kilogram of water. And then you plot on the Y scale the temperature. So let's start out, you add no heat, and it starts at negative 40 degrees C. It's negative 40 degrees C. Water, negative 40 degrees C. What state do you think it is in? A kilogram of it. Ice. It's solid. It's a chunk of ice. Okay, this is one of those concepts. If I have a chunk of ice, it's cold, but I can have that chunk of ice at negative 40 degrees C, negative 20 degrees C, 0 degrees C. It's all solid. Is some of that ice colder than the other ice? It is. So you add some heat. You don't have to add that much heat, and it warms the ice up. But you do have to add some heat. How much heat do you have to add? Well, first of all, I'm going to get it up to a temperature of 0 at 1 atm. This is all 1 bar, 1 atm, close enough. So once it gets up to 0, what does the chunk of ice start to do is you pump more heat into it. It starts to melt. And now you have to pump a lot of heat into it before it turns into liquid. So all of this here is ice, solid ice. This is two-phase, it's melting. Now it's saturated liquid. Now if I pump more heat into it, it's going to increase the temperature of that liquid. And now as I pump more heat into it, the temperature goes up, 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 until we get to 100. Now it's saturated liquid on the other end. If I pump more heat into it, it's going to go into vapor. And so then you pump heat into it. Look how much heat you have to pump into it to turn all of it from liquid to vapor. Can you get a good visual image of how much heat you have to pump in? It's a lot. So does it matter the amount of water you have? I put it all per kilogram. Oh. So you just scale this, say 2 kilograms, double it. So, and here's some values. To melt it, it takes 333 kilojoules per kilogram at 0 degrees C. To boil it, it takes 2,260 kilojoules to boil it at 100 degrees C. The length of this line on the x-axis is around 2,260. The length of this line on the x-axis, 333. Now you say, well, what about in this region? Well, we typically characterize it by a specific heat. Specific heat of ice is around 2 kilojoules. I know it's not accurate to 3 significant digits. It's good enough. 2 kilojoules per kilogram. In the liquid phase, the specific heat, that's the slope, is 4.2 kilojoules per kilogram. And out in the vapor phase, it's back to around 2. Now, I know that I'm telling you it's proportional to the slope, but what you do is you say Q is equal to C delta T. What I have on the y-axis is delta T. What I have on the x-axis is Q, so the slope is the inverse of the specific heat. It's the inverse of that specific heat, okay? It's steeper and not as steep because the slope is 1 over 4.2 versus 1 over 2. And over here it's 1 over 2. The idea is there's a lot of energy associated with changing phases. A lot of energy to boil it or condense it. A lot of energy associated, but not as much, of melting and freezing. So hopefully this plot makes sense and it gives you a good perspective on it. What would happen if I changed this to, I don't know, 10 bar? Well, it starts to narrow the amount of energy. This would be less right in here. Because as you go up toward that point at the top of the dome, I forgot the name of that point at the top of the dome. The critical point, what is HFG at the critical point? 0. And this is HFG down at 1 bar for water. Ideal gas. There's a lot of things to know about an ideal gas, but when we say we have an ideal gas, it obeys the equation or can be described by this equation. PV is equal to RT, as well as U is a function of temperature only. We confirmed that by somebody's experiment, Dalton's experiment, Avogadro's experiment. Whose experiment? Joule's experiment. And what he showed was that the internal energy, not a function of volume. The internal energy of a true ideal gas, not a function of pressure. They ruled those out. The internal energy is a function of temperature. Temperature, temperature, temperature. Also, from the definition of H is U plus PV. True? Is that the definition of enthalpy? Well, guess what PV is equal to? RT. So it's equal to U as a function of temperature only plus R times T. Now, I know T is a function of temperature. It's like obvious, right? But what about R? Is R maybe a function of temperature? Is R maybe a function of pressure? Is R maybe a function of specific volume? What is R a function of? It's a hint in the name. It's the ideal gas constant. You said, well, hold it. It's R is equal to R bar divided by the molar mass. This is the universal gas constant, 8.314 kilojoules per kilomole Kelvin, and this is the molar mass. Are either one of those a function of pressure? Are either one of those a function of anything? No, they're constants. And so R is a constant. That's how you can conclude that H, likewise, is a function of temperature only. Joule's experiment confirmed U is a function of temperature. By definition and ideal gas equation, H is a function of temperature only. Is this true for steam or true for only ideal gases? Only ideal gases. That's right. Now there's another thing if I haven't pointed it out to you before. R bar, somebody writes it like this, 8.314 kilopascals times meter cubed per kilomole Kelvin. Professor, I think they made a mistake because it's 8.314 kilojoules per kilomole Kelvin. All right, I give up. Professor, which one's correct? They're both correct, aren't they? And because 1 kilopascal times 1 meter cubed, you do the unit conversion, is equal to 1 kilojoule. How many people already discovered that? That is so helpful. That is such a really, really helpful unit conversion. Why? Because sometimes we need to use it to get back some pressure or volume. If you're going toward getting the units of pressure and volume, use this form. Right there's pressure, right there's volume. Sometimes you're using it for energy. Use this form. Right there's energy. See? How many people have, put in the kilojoules and then said, oh, I need to now turn it into pressure, and then they put in a unit conversion. Right? We don't want to show you the shortcuts too early in life. But this one's always been available to you. It's in your textbook as well. But this is a very, very useful unit conversion. Now, those specific heats, just because C was a function of temperature only doesn't mean it can't be a pretty strong function of temperature. Now, so we look at this plot, and they put C sub P bar divided by R bar on the y-axis. Okay, what is this bar doing on top of the C sub P? Is it average? I learned that maybe in statistics, right, or some other math class. If I wanted to know the average, it would be X bar. Oh, that's the average X. The mean or something like that. But is that what they use the R bar? The bar over here? No, it is, help me, it's on a molar basis, right? It's going to be the units on this C sub P bar. C sub P have units of kilojoules per kilogram Kelvin. C sub P bar has units of what? Kilojoule per something Kelvin. What do you think? Kilomole. How can I jump back and forth between C sub P and C sub P bar? Use big M. Use the molar mass. What were the units on a molar mass? Kilowatt per kilowatt. Kilogram per kilomole. So how do I go between C sub P bar and I want to go to C sub P? So if I take that and I divide by the molar mass, do I get to C sub P? So now this is R bar. Somebody says, why didn't they plot C sub P divided by R? It's the same numeric value. 5 C sub P bar divided by R bar is the same as 5 C sub P over R. So they could have thrown out the bars on both of these right here. Just go whoop, gone, whoop, gone. Now that's the y-axis. The x-axis, it's temperature. They give it to you in Kelvin or they give it to you in Rankine. Why didn't they pick one? I don't know. Why didn't they give all 4? I don't know. If they gave all 4, where would be degrees C? What would this be down here? Would it be negative 273? And where would be the boiling point of water? Would it be kind of in this vicinity or this vicinity? Yeah, way down in here, true? Right? Okay, so anyway, boiling point, all that would be way down in here. Now let's do this. I noticed some groupings of these curves because all of these are for ideal gases. All of these curves are ideal gases. I have a group up here, I have a group here, and I have a group right there. 3 groups. Let's take a look at the first group, Group A. Who's in it? Argon, neon, helium. Let's take a look at the Group B. It's oxygen, carbon monoxide, and hydrogen and air. What about this group? Carbon dioxide and water vapor. So what do I notice the pattern? What's true about the Group A? Everybody in that group is a noble gas, a monoatomic gas. It floats around by itself. Everybody in Group B is a diatomic gas. They float around in pairs. The O doesn't go by itself. It's with another O, O2. N doesn't go by itself. It goes as N2. There's a little sharing of electrons between them two. There's some together. And up here, 3 in a molecule. Carbon dioxide, carbon with 2 oxygens in that molecule. So which one has the strongest variation of specific heats with temperature? The more complicated molecule. Which one doesn't have a variation of specific heat with temperature? All of the monoatomics. They're flatline, meaning no matter if I come in and evaluate at 1,000, 2,000, 3,000, 4,000, 5,000, I get the same value. Does that mean it's strongly temperature dependent or not temperature dependent? It is not. It is a constant. We're going to be looking for tables of properties because they're nice, and they put a table of properties for air, and you can just go into the table and you can get the internal energy or the enthalpy at this temperature, this temperature, this temperature, and it varies. It's not a straight line. But then some student will say, wow, I've been given a problem with helium. I want to go find the temperature dependent properties for internal energy and enthalpy of helium. And they look through the book. And what do? Can they find properties, that table of properties for helium? No, they can't. And so what you have to do, it would be a boring table because it's just an increment. It has no, it's just a linear relationship. So they said, no, we're not going to make a table like that. You just have to use the, if you wanted to calculate the change in enthalpy, let's say the enthalpy at temperature T2 minus the enthalpy at temperature T1 for helium, you just go and you get the specific heat of helium and you go T2 minus T1. Boom, done. Somebody says they're so frustrated. They come over here and they say, what is that value of C sub P bar divided by R bar for helium? What's it look like? Does it look close enough to 2.5? Yeah. All right, so we grab 2.5, okay? But then they say, but I want C sub P. It's going to be, can you see it? It's going to be C sub P divided by R times R. That's C sub P. This ratio is 2.5. What is this R? R bar divided by the molar mass for the helium, or the molar mass of the argon, or the molar mass of the whatever else, neon. So that's how you get that specific heat. How about this? Oh no, I wanted U2 minus U1. Well, it's C sub V, all right, times T2 minus T1. Did I cover that? What is the relationship between, for an ideal gas, I need to come back here real fast. Let me see if I can tuck it into this corner. What is the relationship between C sub P, C sub V, and R? Where did this come from? It's just a relationship between two properties and another property, C sub P and C sub V, for a true ideal gas. Okay, how do we get this equation? There's probably a couple of ways to get it. H is equal to U plus PV. Is that true? Can we start there? Is that a good equation? U plus RT. Is that still good for an ideal gas? If I take and I differentiate this with respect to temperature, I can do an ordinary derivative because H is only a function of temperature and U is only a function of temperature. But what does this turn into? dH dt, that's C sub P. du dt, that's C sub V. Derivative of RT with respect to T is R. There you go, that's the equation. So the difference between the specific heats for ideal gas is just R. Professor, should that be R bar? You can put R bar, R bar, R, you can put the bars on all of them, or you can take them off. Come back to here and you say, well, they gave me a plot of C sub P over R, but I need C sub V over R. I need to scroll down a little. So this C sub V is equal to C sub P minus R. Is that C sub V? And this is C sub P divided by R minus 1 times R. That's a times R. You just said, hey, this was 2.5 for the monoatomic ideal gas. I subtract 1 from the 2.5 and then multiply by R. So that's how you get C sub V. All right, let's continue on. Not only do they give you a plot like on the previous slide, but in this table, they give you a polynomial expression for the same thing, C sub P bar divided by R bar. That was on the y-axis as a function of temperature, which was on the x-axis. So it's a polynomial expression. One thing to note, can I put in a temperature outside of this range? You shouldn't. When you have a polynomial fit from numerical methods, what happens when you use it to extrapolate? It oscillates wildly, and it's no good. Do not use a polynomial for extrapolation. And to go ahead and plot it below 300 and above 1,000, and you'll watch it start to really shoot around and wiggle. Here are the coefficients for carbon monoxide, dioxide, all these, and down at the bottom, all they say is monoatomic gases. What is the coefficient of beta for a monoatomic gas? What about gamma for a monoatomic gas? What's the only non-zero alpha? The beginning, it's just a constant, 2.5. So you say that plot looked like it was 2.55. I know. Go back and get the graphics designer, slap his hand, say, get that red line straight on 2.5, right? I mean, look at how many people looked at that and said, I think it's a little above 2.5. I agree, he's a little off on the plot there. But here it is. Is that clear enough? It's 2.5. So this table, you come and you remember, oh, a monatomic gas such as helium. Oh, I forgot the name of this one. Ne. Neon. I forgot the name of Ar. Argon. Over a wide range of temperatures, very nearly equal to 5 halves, 2.5. We don't really use this analytic expression much. It's just too complex. What they did do is they gave us a table for a lot of the properties, not all of them. Let's take a look, though, at air. Temperature is your main input. And if you wanted to get enthalpy of internal energy at 260 Kelvin, there it is. At this temperature, there it is. Notice, this table's good outside of the range of that analytic expression that was on the previous slide. Now, what about S0? Forget it. It's dealing with entropy later, chapter 6, next chapter. What about all this when you're undergoing a process where the change in S is 0? Later. All of this is later. But temperature and enthalpy and internal energy are given. Notice they come up here and they say the temperature is in units of Kelvin. H and U are in units of kilojoules per kilogram, and S0 is, those are the units, but we'll pay attention to that later. Also, to save space, what did they do right here? A second whole set. I mean, it's so you come down and then you need to look back up, because right down here probably is 440, and then it goes to 450 and then down. Then it goes to the next page. Okay, so sometimes students will not see these temperatures over here. Does this account for the temperature-dependent specific heat? Yes. If you go and you say, I want to deal with carbon dioxide or carbon monoxide, or water vapor or oxygen. And there's another column, I think it's nitrogen. I truncated it. Yes, they have it. They have enthalpy and internal energy as a function of temperature going down. But notice they put it on a H bar. It's hard to see, I'm sorry, but it's H bar, meaning per unit amount per kilomole. So the units are kilojoules per kilomole on the enthalpy. Notice they tell you that right up here. It's kilojoules per kilomole. Sometimes it's really useful to read the header, of the table. It gives you a lot of information, okay? Don't worry about S bar naught. We'll deal with them later. So that's of selected gases, not all the gases. Well, we have the real gas compressibility factor Z. And so if you take the ideal gas equation, PV is equal to RT, it starts to deviate as you get close to the top of the dome. You start to get where it may get close to condensing, where the gas molecules aren't very far apart, but they're close together. And so what they put together is they say, well, we'll have a fudge factor called the compressibility factor. As long as we can make Z not equal to 1, we'll move it around as it gets close to the dome, then we can still make this equation work. So this is a modified ideal gas law. It's for quote-unquote real gases, and it has that compressibility factor Z in it. Often they just say Z is equal to PV divided by RT. They plot it as a function of it's the next plot, of some reduced temperature, reduced pressure, and then you unravel it to get Z to apply it in a particular problem. So here is the compressibility chart where what did they plot on the y-axis? Z, the compressibility factor. Notice they said this is PV bar divided by R bar T, or take the bars off the V and off the R. It's on a molar description or a mass description. Just to help remind you, why didn't they do that on the previous plot, Professor? Why didn't they come back here? I mean, they did it on that plot. Why didn't they say, right here on this axis, C sub P bar divided by R bar, or C sub P divided by R? Maybe in the 12th edition of the textbook they will. But in our whatever edition we have, they didn't. So it's a little helpful that they did it here to make it really clear. And what do we have? Reduced pressure along the x-axis, and we have lines of constant reduced temperature. This is for methane, ethylene, ethane, propane, all of these substances. And they have an average curve fit. So it's a curve fit. This is not good to 18 digits, significant digits. Not even good to like 3. It's just a curve fit. But T sub R, the reduced temperature, is the physical actual temperature that you're evaluating at divided by the critical point temperature, TC. And the reduced pressure is the actual pressure divided by the critical point pressure. We're done with Chapter 3 covering material now, okay? I was going to cover some software, but I decided I'll delete it, okay? Because I don't test you with the software. It would have just been an enhancement for the broadening of your educational experience. Professor, just tell me what's on the test, right? I'll broaden my educational experience later in life. I want to pass the class first. So that's not on the test, so we skip it. We already covered polytropic processes. That's a fancy name for any process where PV to the N is equal to a constant, and N can vary. True? 1, 1.1, 1.3, something like that. N can vary. Or usually it's given to be a constant, but a different problem could have a different N. That's what I should say. It doesn't vary as volume varies or pressure varies. It's a constant for that problem. And we already did this. We plot those, and we did the calculation of the work. The integral of PDV for different polytropic coefficients N. There's a whole couple pages you need to read the textbook. So we covered a lot of material in properties. It's a challenging chapter. Let's solve some problems. Here's an example of a multiple choice question. I want you to write down the answer to this question, okay? So what are the units of work? There it is. And then once you make the answer to that one, what's the minimum temperature possible for liquid oxygen? And I'm going to pause and walk around and see what answers I get, okay? All right, so everybody, I think, worked through this one. Some people, they wanted to give me this answer. What is that answer good for? Not work, it's good for power. Power. This is the right answer for work, true? And this one, we're just going to let you struggle with. The big hint is, if you go below that temperature, you are going to get into solid. It's going to be a solid. And you need to look at a PVT surface. The diagram, the PVT diagram. Yes, sir?
Or just the PT diagram.
A projection. The PT diagram would help as equally well. A PT diagram would help equally well. I stop there and move on. I'm going to now pause and let you guys struggle. All right, so how many people are still struggling? Everybody's got it? Well, you have to remember that the pressure gauge plus pressure ATM, the local atmospheric pressure, is your pressure absolute. The initial tank pressure is 400 kPa with a local of 100. So what's the pressure initial state 1 absolute? It's 501 or close enough to 500 kPa, true? And then it's filled so that the final absolute pressure ends up at pressure 2 absolute is 950. How much did it change? 450. It went up 450 kilopascal. That was, what was the increase in the pressure? All right, some true false. I'll pause, let you work on it. All right, so let's just try to work through this. For a closed system, it's impossible to have a heat transfer without a temperature difference. Well, what do you think? True?
True.
False? We got some truths and some falses. I know it's hard to navigate because the impossible and without. Maybe I should change it around to try to get rid of the negatives. If there is a heat transfer, is there a temperature difference? Okay, how many ways did you transfer heat? Conduction, convection, radiation. Can there be another mode of heat transfer that they talked about? Or were there only those three modes? There's only those three modes. Now, for each of those modes, can you have conduction without something being hot and something being cold? Convections, something have to be hot, something have to be cold. Radiation, something have to be hotter than the other. In the net exchange in the radiation equations, I know photons are being emitted from a surface at all times if it's above 0 Kelvin, but it's typically in the presence of another surface. That then is net exchange. That net exchange is proportional to temperature to the fourth difference. It's a temperature difference. You need a temperature difference. Can I have a heat transfer without a temperature difference? No. This is maybe too many impossibles. But it is impossible to have a heat transfer without, you have to have a temperature difference. What about this one? Somebody went like this. True? That's an illustration of closed system, paddle wheel, work transfer across the boundary, but no volume change. So, all right, so I think a lot of people have already worked on this one. So what does adiabatic mean? Which one? A, B, C, D, E? So it's E. Do you agree? Very good. And then isobaric, what's it mean? C, constant pressure. Very good, right? What did I say? Morale booster? Or regain your confidence a little bit. So let's press on. Automobile traveling 75 kph. What is kph? Kilometer per hour. Subjected to an aerodynamic drag force of so many newtons, 820 newtons. What is the automobile power required to overcome this resistance so that the vehicle travels at constant speed? All right, so what do we recall? That the power, if you like to use W dot for the power, when you have a moving object, you have a force that has to overcome or balance the drag force, okay? And that force that it has to overcome the drag force is multiplied by the velocity, and that gives you the power. So force times speed. Okay, it's not. I'm not interested in the vector product, but you could put it the vector notation as well. So we have a force of 820 newtons, and we have a speed of 75 kilometers per hour. And then do the units carefully. An hour is 60 times 60. Is that how many seconds are in an hour? And then a kilometer, you can leave the kilo there if you want, just don't forget the kilo. If you do a Newton times a meter, what do you get? Joule. A watt is a joule per second. That's the one I want. And so this will give you the kilo watt. Answer true. Okay, so people worked this out and they got 17 kilowatts. Very good. All right. Liquid water, you have a mass of 1.5 kilograms of liquid water. It's initially at the temperature of 20 degrees C. It's heated to a final temperature of 90 degrees C in a pot that has a 1200 watt electric heating element inside. So it's like this with a little heating element like that. The specific heat of water is 4.2 kilojoules per kilogram degree C. The heat loss from the water can be neglected, so Q dot is equal to 0 between the water and the surroundings. Determine the time it takes to heat the water. All right, so quite a few people solved the problem. There's multi-steps to it. I would do the first law where you have Q 1 to 2 minus the work 1 to 2 equal to M U2 minus U1, something like that. Does that look like a good first law?
Yeah.
Okay, it depends how you want to count for the heat transfer. Either you say this is the work electric coming in, but it's not in, it's with the minus sign, or you just say that the system is the water without the heater, and the heater turns electricity into heat, which comes into the water. Maybe that's easier conceptually to visualize, but one of them. Either your system includes the boundary where electric power is penetrating it, or the system includes only right at the surface of the heater and heat's coming into it from the heater. Okay? So you're taking the mass of 1.5 kilograms. I should put my units in there, kilogram. And you multiply by the specific heat, 4.2 kilojoules per kilogram degrees C. And the temperature change, it ended at 90 and it started at 20, so there's a 70 degree C temperature increase. Make sure your units always work on this stuff. So that's how many kilojoules of energy had to come in. Let's say it comes in the form of a heat transfer into the system. Whoops, 1 to 2. So Q1 to 2 is so many kilojoules. How many people, what number did you get for the kilojoules? 441 kilojoules. Okay. Now, it's coming in at a constant rate, so Q dot times delta T or the integral of q dot dt would be how much comes in from 1 to 2, 1 to 2, true? And it's coming in at a constant rate. Q dot's 1200. So the time it takes is equal to how much comes in, how much I need to come in, divided by the rate at which it comes in. So 441 kilojoules divided by 1200 watts, which is a joule per second. True? And then we have 60 seconds is a minute to convert from seconds over. Watch out for that kilo. You can do this. You can put it right there and put a kilo right there and then cancel the kilos if you like. So what did we calculate? 6 minutes? Thumbs up? Very good. Let's press forward. What is the approximate mass of 1 liter of engine oil? Approximate. You don't need to look in the tables for this, okay? And then, what is the lowest temperature in degrees C? I'm going to pause and let you answer it. The density of oil is around 900 kilograms per cubic meter. All right, that help? What's the density of water? Liquid water? Around 1,000 kilograms per cubic meter. Are they close enough to each other? Close enough to each other. So what answer do you get for the first one? A, B, C, D? Which one? D. And then what is the lowest possible temperature in degrees C? Which one? Very good. Are the pressures in the tables absolute or gauge? And the pressure of 40 psig, is that a pressure of 40 psig is greater than 40 psia? True or false? All right, well, how about this one? The absolute pressure are in the tables. The tables are the steam tables. The tables are for refrigerant 134A, the refrigerants for ammonia, the refrigerants for propane. There's a lot of tables, right? And there's pressures in there. And a lot of times they just say kPa. Is that absolute or gauge pressure? Absolute. Now, the way to do this is you say pressure, let's define this as pressure 1. Pressure 1 is 40 psig. Let's say this is pressure 2. Pressure 2 is 40 psia. All I have to do is convert pressure 1 to the same scale, or pressure 2 to the same scale as the other one. So if I wanted to convert 40 psig to psia, what do? Add atmosphere. Atmosphere is about how many psi? About 15. So 40 plus 15. So the first pressure is 55 psia. Now is the question a little easier? Which was a higher pressure, 55 psia or 40 psia? The pressure of 55 psia is greater than 40. I agree. If the direction of energy transfer is shown by an arrow on a sketch of the system, then work is regarded as positive in the direction of the arrow. And then the next one, a shaft having 50 newton meters of torque rotates 1 revolution. What was the work transfer? All right, whenever you have a sketch in the system, even though it's normally work out as positive, if they show the work in, that's now the direction. The sketch and the direction of the arrow on the sketch trumps everything. True? Just like in statics in the free body diagram. If they had an XY system like this, and they put the force going that way, that was the positive direction of the force. True? True. All right. So this, true. So we have the torque times a rotation gives me work. That's just like a force times a distance gives me work, true? So you just have to do the 50 Newton meters of torque, 1 revolution, but I don't like those units. I have to convert. A revolution is how many radians? 2 pi. Then also I do convert this Newton meter into a joule because now we're talking about work, energy transfer. So whatever that answer is, what is it? 310? Refrigeration system removes 25 kilojoules of heat from a cold body, rejects 33 kilojoules of heat to a hot body. The coefficient of performance is, make a sketch. There's your system. It's a refrigeration system. There's my cold body. There's a heat transfer from the cold body. Takes work from the surroundings to run a refrigerator. And you dump heat to the hot body. So the coefficient of performance, you have to remember, coefficient of performance for a what type of system? Refrigeration system is what I desire. I desire QC over what I have to pay for work. So let's just say that the QC was 25 kilojoules. The QH, that's what's rejected to the hot body, is 33 kilojoules. What's this work? This is an in, this is an in, only one out. 8 kilojoules. So it's what we desire, 25 divided by 8. There you go. All right. Last one, I don't think I have much time. Electric motor draws a current of 10 amps. And it has a electromotive force of 120 volts. That's the voltage supplied to that. The output shaft, so here's my electric motor. The output shaft is rotating. It has a torque of 8.3 Newton meter in the shaft. And it has a rotational speed, I'll call it omega, of 1,200 revolutions per minute. Operates at steady state. Determine electric power input or required. I didn't give you multiple choice on this one, so all you have to do is do the electric power input. W dot electric is the electromotive force times the current. So it's 1200 watts. Amp times volt is a watt. Of electric power coming in, W dot electric of 1200 watts. What is the power developed by the output shaft? W dot shaft is equal to the torque times its rotational speed. Got to get the units right. 8.3 Newton meter, and then you have 1200 2 pi radians per 60 seconds. Newton meter, joule, joule per second, watt. So this turns out to be something. I don't know what it is. It's less than 1200. Then you have some stray heat transfer off the hot motor. You ever seen a motor run? They're hot. In a cool room, they're dissipating heat into the room. Q dot off of the surface of the motor. That's going to be W dot electric in minus W dot shaft out. Energy balance for this control volume around the motor. What is the efficiency of the motor? The efficiency of the motor is what you desire. What do you desire? You desire that W dot shaft, that power out the shaft. Over what did you have to pay for to make the thing run? W dot electric. Will it be 100%? No, it'll be down 97, 95, 93, 87, something percent. Thank you.